So I'm going to give a talk on Mars Direct, Humans to the Red Planet in a Decade, explaining how I think we can do that, and I think we will do it in something close to this method. Now, this is a lot to try to explain in half an hour, but fortunately I have written a book on this and related subjects called The Case for Space, and we've got a couple of boxes of them here. And so if after this talk you think this is interesting to you, they're going to have them in the bookstore at 5 o'clock, and you come there, you buy them, I will sign them, everybody wins. There you go. All right, so Mars Direct, Mars in a decade. How? Those of you who read about this have probably seen ideas like this illustrated. This is a NASA design for a giant interplanetary spacecraft. It's very big. You can see Mars is here for scale. Okay, so this is actually very similar to a Star Destroyer from Star Wars. So it has heritage, I guess. But clearly, if that is what is required to send humans to Mars, we're not going to do it in a decade. But that is not what is required. What we do need is a heavy lift vehicle. Now, that is not science fiction. Here, you're looking at a photograph here from 1970 of Apollo, the Saturn V heavy lift vehicle that could lift 140 tons to Earth orbit. Now, that is a half century ago. Right now, 2 other heavy lift vehicles are in development, one by NASA of something different in detail, but not fundamentally different from this, called the SLS, an alternative heavy lift expendable vehicle. But the other, very different, except in capacity, it's the same, which is the Spacex Starship being developed by, Elon Musk and his team, and they are moving very rapidly on this. And this is a fully reusable heavy lift vehicle, but also with about the same capability as a Saturn V, except it will be at least a factor of 10 cheaper per launch, because instead of being thrown away after every launch, it will be reused. Now, if you had a vehicle of this general type, how do you do the mission? Because, well, what's that? Okay, go back. Here we are. All right. This is a mission sequence chart. Okay. Because I believe the Starship, okay, Musk says he's going to have it flying this year. I think he's going to have it flying by 2022. But whether it's this year or 2 years from now, it doesn't make a lot of difference. Okay, in the first year of active flight operations, which we'll assume is say 2029, we launch one of these rockets, and we use it to send a single automated payload on a direct trajectory to Mars. Now, what is this payload? Okay, the payload flies out to Mars. Musk talks about sending the Starship all the way to Mars. You could do that, but I wouldn't. I would just use it to send things up to Earth orbit and have an upper stage send the payloads from there. That way you get to use the Starship again and again much faster. But anyway, we send the payload to Mars. It takes 8 months to fly to Mars. Then it deploys an aerobrake that is used to make friction against the Martian atmosphere and captures it from an interplanetary trajectory to one that is in orbit around Mars. And then after we make sure that everything is good and the weather is good, we bring it into the atmosphere more deeply. The aeroshell slows us down to subsonic speeds. Then we send out parachutes, come down slow, and put ourselves down soft on the surface of Mars. Okay, with rockets. And this is pretty weird. There we go. So what is the payload that we have landed on Mars? It consists of a number of things. the primary object is the Earth Return Vehicle, which is a little rocket ship for flying back from Mars to Earth. It has a small cabin here, so you can see it's 5.5 meters tall and about 4.5 meters wide. It has 2 decks. It has modest quarters for a crew of 4 for a 6-month voyage from Mars to Earth in the final stage of the mission, but no one's in it now. Then below the vehicle, here are 2 methane-oxygen propulsion stages. However, they're not fueled with methane and oxygen. There's nothing in them except some hydrogen in the lower stage tanks that will later contain methane, about 6 tons of hydrogen. And then slung below this vehicle, what is this? How does this go? Okay, not shown in this diagram is a little truck, runs on methane and oxygen, and in the back of that truck is a little nuclear reactor with a power of 100 kilowatts, okay, which is about the same amount of power as the engine of a medium-sized automobile. Okay, so it's not like a nuclear power plant that powers a city. It's just something that could be put in the back of a truck. And then after you land, the truck is telerobotically driven a couple of 100 meters away, unwinding a cable off the back of it as it goes, and then the reactor is put down on the ground, preferably in a crater or other depression in the terrain, and then it's turned on to provide power at the ship. And what you do then is you run a pump and you suck in the Martian air, which is mostly carbon dioxide gas, here. You react that with hydrogen from Earth. You produce methane and water. Okay, this is basic chemistry, been known since the gaslight era. Methane is your fuel. The water you take and you electrolyze into hydrogen and oxygen. The oxygen is the oxidizer to burn the fuel. The hydrogen goes back and makes more methane. And to get additional oxygen, we have another reactor in which we take carbon dioxide and we split it into carbon monoxide and oxygen. The oxygen we keep, the carbon monoxide we vent as waste. You can do that on Mars. There's no environmental protection agency there. And what you've managed to do is turn your 6 tons of hydrogen from Earth into 108 tons of methane and oxygen propellant on the surface of Mars. Now, there is water ice on Mars, and in later missions, once we have identified exactly where it is and brought the water ice back to the base, we won't need to bring hydrogen to Mars at all. We'll be able to get the hydrogen from Martian water. But to start with, we'll bring the hydrogen because it's only 5% of the weight of the propellant that you make with it. Okay, so, and this chemistry has been all well demonstrated. In fact, that's me a number of years ago with the first machine that did all this, although the chemistry that we based ourselves on is over 100 years older than that. So now you have a fully fueled Earth return vehicle sitting, waiting for you on the surface of Mars. That being done, at the next launch window, which in this case would be 2031, we launch 2 more rockets. One sends out another Earth return vehicle, just like the first. The other sends out a habitat with a crew of 4 astronauts in it. Now, because our return ride is waiting for us on Mars, we don't need to fly to Mars in an Imperial Star Destroyer. Okay? We don't even need to fly to Mars in a comparatively modest Millennium Falcon. We can fly to Mars in a tuna can, and that is much easier. Tuna cans, of course, have been demonstrated for packaging purposes, although this is larger than the one you probably see at your grocery store. It's 8 meters in diameter and about 6 meters tall, so 2 decks, each 3 meters high. The lower deck is kind of a workshop. The upper deck is where the people live. Here's one layout of the upper deck. okay? What you see here are 4 little staterooms for each of the astronauts, a science area, exercise area, kitchen, wardroom area, and in the center is the solar flare storm shelter. Now, this is worth talking about for a minute. There's 2 kinds of radiation in interplanetary space: solar flares, cosmic rays. Solar flares are something that happens unpredictably. Occasionally, you'll get a big one about once a year, but you could have 2 in 1 year and none the next year. Okay, they come and they go. And in the course of 4, 5, 6 hours, deliver enough radiation to kill an unshielded astronaut. Well, that's bad. But the good news is that the kind of radiation that solar flares are made of are protons with energies of about 1 million volts. And that can be stopped by 10 centimeters of water, or things that from the nuclear point of view are essentially the same thing as water, such as food, or things that water and food become as the mission proceeds. And we can basically pack enough of that material in a central area so that it's shielded, and when the solar flare happens, the alarm rings, everyone goes in here, they're stuffed pretty tight for a few hours, but then the all clear rings, they come out, and it's done. And that will happen maybe twice in the whole mission. So that's how you deal with solar flares. The other hazard is the cosmic rays. Now, they don't come from the sun, and they have energies not of millions of volts, but billions of volts, 1,000 times more energy for each particle than solar flares. So you can't stop them with centimeters of shielding, you need meters of shielding, and we don't have that much mass. But the good news is that the amount of radiation is modest, okay? These doses here are in rems, 100 rems to a sievert, which is the European unit. But anyway, what you're seeing is the radiation dose that could be expected on a round trip to Mars is between 0.5 and 1 sievert. And in fact, a variety of astronauts and cosmonauts have already gotten that radiation dose on the space station, and there have been no radiological casualties. In fact, a radiation dose of this magnitude represents about a 1% risk of getting cancer. And so it really is a modest portion of mission risk. The thing that people don't talk about that much, but should, the thing that actually has affected the health of astronauts in space is not radiation at all. It's zero gravity, and people being deconditioned by zero gravity on the space station. Now, this is not fatal. No one has died of it, but astronauts, and especially cosmonauts, have been severely deconditioned. The cosmonauts more so because they don't do the exercise program on the space station. They drink too much. But anyway, the there is a way to avoid this deconditioning, and that is to create artificial gravity, which you can do by extending a tether between the spacecraft and the upper stage that threw it to Mars. This tether is about 1.5 kilometers long. You spin this at 1 revolution per minute. We can make Mars gravity in the habitat. If we spin it at 2 revolutions per minute, or a little less than that, we can create Earth gravity. And that is how we can avoid the deconditioning, which once again is not something that endangers the lives of the crew, but will reduce their effectiveness once they get to Mars. We don't want them to be weak. So it takes 6 months for them to reach Mars. That is, we send them a slightly faster trajectory than we send the cargo. And then when they get close to Mars, we fire a pyrotechnic that cuts the cable. This goes away. They go and they land at Mars, at the landing site, where a fully fueled Earth return vehicle waits for them. Now, we've been at that landing site for 2 years, okay, with rovers, and they have photographed the place, identified the best possible place to land, put a landing beacon there, and we have the best pilot in the world flying this thing. We should be able to land right there. But if they don't, if they land 50 kilometers away, which would be a very large landing area, we're still okay because we have with us in the lower deck of the HAB a pressurized ground rover that runs on methane oxygen, and it has a one-way range of 1,000 kilometers. So it would take an enormous landing area to land outside of its range of action. But let's say even that happens, if they don't land here or here or here, okay, if they land on the wrong side of the planet, okay, which would represent a problem with the pilot selection, we're still okay because we have another Earth return vehicle following us out to Mars. And if they do land over here somewhere, we could just send this one to land near us. So that is a third level backup on the mission. And finally, as a fourth level backup, if we can't land accurately, if we can't get there with our ground rover, if we can't get there with the second Earth return vehicle, we have enough supplies with us in the ship that they can last 2 years, so that if everything else fails, at the next launch window, more supplies and another Earth return vehicle can be sent out to them then. So there's a 4-layer defense of the mission, and each layer involves actually carrying off the mission. But let's say it works as it should. Okay, so we don't need the second Earth return vehicle for us. We can land it somewhere else, which in principle could be anywhere. I like landing it a few hundred kilometers away so that if the crew does need it, they can drive to it. But mostly it's there to be the return vehicle of the next mission, which will fly there in 2033, along with another Earth return vehicle, which is their backup, but which otherwise opens up the third landing site. So the idea is 2 launches every 2 years to have a continuous program of exploring Mars. Now, when we were launching space shuttles, we launched an average of 6 a year. So this is using 1/6 of that capability, heavy lift capability, to support this program, which means at the same time we do Mars, we can do the moon, we can go to lots of places. This is not going to monopolize the whole program. So this is an actual photograph recently returned to me from the future, showing the Mars base. So here is the Earth return vehicle, the cabin, the upper stage, the lower stage. Here is the propellant-making plant built into the lower stage. Here's the reactor that's powering it. Here is the HAB module, the upper deck where they live, the lower deck, a workshop garage for the ground vehicle. Some solar panels, which can provide backup power if we have to turn the reactor off. We can also run the engine of the rover to make backup power, or the light truck, which is probably hard to see, but it's sitting over here. That was used to deploy the reactor. It's a backup vehicle for this. And this here, this is an inflatable greenhouse. It is not a mission-critical element. It is an experiment in growing crops on Mars, in Martian gravity, in Martian soil, Martian sunlight, Martian water, for learning how to do that for the benefit of future missions and future bases. Now, we're going to be on Mars for 1.5 years. Why 1.5 years? Because that's how long it will take for the planets to move around to give us an open window to launch back to Earth at the end. But it makes sense if it takes 6 months to fly to Mars and 6 months to fly back, you might as well spend at least that much time on Mars actually doing exploration, which is the real goal and purpose of the mission. So it's 2.5 years away from home, 1.5 years on Mars, 6 months out, 6 months back. And what are we going to explore for? Well, there's a lot of things that people are interested in Mars about, all sorts of scientific questions, but there are 2 that make it of interest not just to professional academics and scientists, but to everyone on Earth, or almost everyone. Anyway, lots of people. The first is the question of, was there or is there life on Mars? Now, this is a real photograph of Mars, okay, taken in 1976 by the Viking orbiter. And what you can see here are dry riverbeds on the surface of Mars. Okay, there are no canals on Mars. That was fantasy. But there really are dry rivers on Mars, thousands of them. And since this time, we've discovered dried up lakes, a dried up northern ocean, massive amounts of water on Mars frozen as ice in glaciers, including some as far south as 38 degrees north, which is the same latitude as Athens in Europe. Okay, so well south of here. Anyway, there's water on Mars, and there was once in liquid form flowing all over the place. And based on the geological evidence, this went on for about the first billion years of the life of the planet, which is 5 times as long as it takes for life to appear on Earth after there was liquid water here. So, if the theory is correct, that life is something that naturally emerges from chemistry whenever physical and chemical conditions are good, then life should have appeared on Mars. And if we go to Mars and find fossils of life that existed there when there was liquid water, we'll have proven that the development of life from chemistry is a general phenomenon in the universe. But moreover, we do know there is still liquid water, not on Mars, but in Mars, underground. Okay, the European Mars Express orbiter with its ground-penetrating radar has discovered subsurface liquid water on Mars, which is a habitable environment for microscopic organisms. So if the life ever existed on the surface, it could have retreated and still be living in the subsurface liquid on Mars, just as there are primitive organisms on Earth. Some of the Earth's earliest microorganisms can no longer live on the surface of the Earth. They still live in the groundwater of the Earth, 3 billion years after they had to abandon the Earth's surface because our atmosphere started having oxygen in it produced by green plants, and oxygen was toxic to them. So they retreated, and they're still there. We could find the Martian life, and we'd be able to, by drilling, it's only about 1 kilometer down. We could drill that deep, bring it up, look at it, and see if Martian life is the same as Earth life, or is it something different? You know, all Earth life at the biochemical level is the same. It uses the same amino acids, it uses the same genetic alphabet, DNA and RNA, for communicating information from one generation to the next. Okay, now I speak English. We use the Latin alphabet. Polish uses the Latin alphabet. They have a common source, although some of the letters have different sounds. It's clearly has the same source. The Russians, they have a different alphabet, but it has a fair amount in common. About half the letters are in common. And the system, the general system of conveying sounds through letters is the same. So in fact, we have a common origin. The Latin alphabet itself came from the Greek alphabet, as did the Russian alphabet. But the Chinese use a completely different alphabet. Completely different. It works, it has nothing in common. It works on totally different principles. It actually doesn't come from sounds. It comes from pictures. And it has a totally different system. So the question is, does all life in the universe use the Latin alphabet of DNA and RNA, or are there ones out there that are using the Chinese alphabet or other alphabets that are completely different, cuneiform, hieroglyphics, you name it, that have a totally separate origin? Okay. In other words, what we're going to find out is the truth about not only the prevalence, but the potential diversity of life in the universe. And this is something that people have wondered about for thousands of years. We find this out by going to Mars. Now, at the end of a year and a half on Mars, we get in the Earth return vehicle, we start it up, and take off, and we fly back to Earth. we leave behind on Mars all this other equipment here, the habitat, the reactor, the greenhouse, the cars, solar panels. Is that bad, leaving all this very expensive equipment behind on Mars? No. We do not need to bring it back to Earth. We have a lot of stuff here already. The idea of Mars missions is to bring as much to Mars as we can and come back with as little as we can, because everything we leave behind on Mars will be available for future missions and future bases. So this is a map of Mars, and you can see little Texas here. Texas is about the size of Poland. Okay, so you can see that Mars is much bigger than Poland. But we could establish a lot of bases and drive from one to the other and keep exploring the same region. We can have scattered bases. So that's an exploration plan. But after a certain number of these missions have occurred, we're going to know the truth about whether there was or is life on Mars. And then the question about Mars is going to shift. You remember I said there were two questions. What's the second one? That's not is there life on Mars? It's a more important question. Will there be life on Mars? Because the most important thing to know about Mars is that it's not just an object of scientific inquiry. It is that. It is the Rosetta Stone for letting us know the truth about life in the universe. But it's something else. It's a world. It's a planet with a surface area equal to all the continents of the Earth put together. And it has on it all the materials needed to support life and therefore technological civilization. And if we can go to Mars and learn how to turn those materials into resources, then we can make Mars habitable. Now, what do I mean by make Mars habitable? Do I mean terraform the planet, like in Star Trek II, The Wrath of Khan, where they unleash the Genesis machine and the barren planet becomes turned into a wonderful planet filled with forests and meadows and butterflies and chipmunks and flying fish? Yes. Okay. That is exactly what I mean. And I believe that humans will do that to Mars someday. And the reason why I believe that is that we are life, and it is the nature of life to take barren environments and transform them into places that are friendly for the development and propagation of life. But that is not what we who are in this room today are going to do. That is a little bit beyond our time, or significantly beyond our time. But what we can do is we can have the honor of making Mars habitable by transforming it not so much physically as intellectually. Because again, the thing that defines whether an environment is habitable for you is whether you can turn the materials that are there into resources that support you. It's what you have up here. Okay? And if we go to Mars and establish a base on Mars and learn how to do that, learn how to go beyond the Mars Direct Plan, which takes the first step by making fuel and oxygen, we learn how to grow plants on Mars. We learn how to make cement, learn how to make bricks, learn how to make glass, metals, plastics, wires, tubes, habitation structures. We learn how to do all that. Then Mars becomes a place that humans can settle, and where in the fullness of time, new branch of human civilizations can develop, which will have the size and the industrial capability and the technological knowledge to be able to completely transform the planet. So that in the end, we don't just bring life to Mars, we bring Mars to life. Okay, now just add, since people talk a lot about the moon nowadays, you can use the same stuff to establish bases on the moon. I won't tell you how, it's in the book. Anyway, so here is the basic tool set you need to establish humanity on 2 new worlds. A heavy lift vehicle, various options for its design, starships, SLS, Saturn V's, okay, a HAB module, an Earth return vehicle, and an aero entry module. And with this, we can do it. So I'm going to conclude, actually, with a quote that you might not be familiar with. and actually only a few Americans are familiar with anymore, but we used to be. Anyway, this is from a book of Plymouth Plantation written by William Bradford. And Bradford was the leader of the people called the Pilgrims. And the Pilgrims were religious dissidents who had fled England, and they had gone to Holland. And they didn't like what was happening to them there. Actually, not because the Dutch were being cruel to them, but for the exact opposite. The Dutch were being very nice, and a lot of the Pilgrims were deserting the faith to just fit in. Anyway, so the leaders of the Pilgrims figured, what can we do? Where can we go? And someone comes up with the crazy idea that what they ought to do was relocate the congregation from the civilized Netherlands into the wilds of North America. Because as hard as it might be, there they could make their own world. There they could have their city on a hill. And he says the following. He says, this proposition, relocation to America, being made public and coming to the scanning of all, it raised many variable opinions amongst men and caused many fears and doubts amongst themselves. Some, from their reasons and hopes conceived, labored to stir up and encourage the rest to undertake and prosecute the same. Others, again, out of their fears, objected against it and sought to divert from it, alleging many things, and those neither unreasonable nor improbable, as that it was a great design and subject to many unconceivable perils and dangers. It was answered that all great and honorable actions are accompanied with great difficulties and must be both enterprised and overcome with answerable courages. William Bradford, 1621. And I put that up there because even though I've just laid out this plan to you, and I believe it will work, and even though this is something we can do in 10 years and not wait a century to put it off on someone else, there is unquestionably risk if you want to do this. But whether you look at 1621 or 1944 or 1969 or any other time you like, there's one thing that is very clear, is that nothing great has ever been accomplished without courage. I'll leave it there. Thank you.